Our topic for today is the difference between the time domain and the frequency domain. You may have worked in the time domain before using an oscilloscope. You may even have worked in the frequency domain using a spectrum analyzer. To truly appreciate the difference between the two, we're going to take a review of phasors as we learned in our previous classes. We're also going to tie everything together with the concept of filters using this tool called Sonic Visualizer, which includes 3 different tools. This first one is in the time domain. You may recognize that. It looks very much like an oscilloscope display. This tool, which we'll see in a moment, is in the frequency domain. It acts as a spectrum analyzer. And this tool is known as a spectrogram. Let's start the music and see what we can see. Okay, that's the target. We want to come to some understanding of what each of these things means. We'll come back to this in a moment once we know a little bit more about the difference between frequency domain and time domain. Let's start here. We want to sketch a waveform. We will let lambda equal 2 meters, and we'll let the peak voltage equal 2 volts. From your note card, you know that lambda is equal to c over f, where c is the speed of light and f is the frequency. You also know that frequency is equal to 1 over the period. If you put those two together, you could say that lambda is equal to the speed of light by the period of the waveform. Given that it's 2 meters, we would say 2 meters is equal to the speed of light, so that's 300 times 10 to the 6th meters per second multiplied by the period of that particular waveform. That would be 2 divided by 300 million. Gives us a period of 6.7 nanoseconds. And now we can sketch the waveform. It looks like this. We're assuming it's a sinusoid, of course. In the time domain, it has a positive amplitude of 2 volts and a negative amplitude of 2 volts. The period, which is the time it takes to complete one complete cycle, is 6.7 nanoseconds. Again, this is what we call a time domain representation, where time is on the horizontal and amplitude is on the vertical. The most common tool that will display the time domain is an oscilloscope. Before I forget, let's go back up here. Using this equation, we could have solved for frequency, and you would have said that frequency is 150 megahertz. Going back to our time domain discussion, we could argue that an oscilloscope will display amplitude. It will display period. You can calculate frequency. If you wanted, you could calculate lambda. You could even determine the shape of a waveform. But that's about where it ends. The oscilloscope is very good for things that are like sine waves or square waves. It's not so good when you're dealing with music. For example, in that opening fanfare, we played this trumpet. If we zoom in on this time domain representation, we can see the signal. This is what a trumpet looks like in the time domain. By the way, notice that time is listed right here. So this is second 6.134, 6.135, and we have an amplitude. So this is 0, We can see we go above and below that amplitude. Now, it's very difficult to describe exactly what we're looking at here, other than to say that that's what a trumpet looks like. It's not a sinusoid, it's not a square wave, it's a rather complex signal. The oscilloscope does not give us a good way of describing that signal. We can get a much better understanding about what makes a trumpet sound like a trumpet by shifting to the frequency domain. The tool that we use is a spectrum analyzer. The display for a spectrum analyzer has frequency running on the horizontal and amplitude in the vertical. Understand that that amplitude is typically in dB or dBm. When we talked about the time domain, we mentioned this signal. It had a period of 6.7 nanoseconds, and we determined that to be a frequency of 150 megahertz. Now, this is the time domain representation. We assumed it was a sinusoid. A sinusoid in the frequency domain is actually a spike. So we see one frequency. If we shifted to the left, there would be nothing. If we shifted to the right, there would be nothing. All we would see is one frequency, in this case at 150 megahertz. This transition between the frequency domain and the time domain is something we're going to talk about in future lectures, especially when we get to the Fourier discussions. Just so we're very clear on this point, we're going to make a little table about our domains. The time domain and the frequency domain. On the horizontal, in the time domain, it's time on the horizontal axis. In the frequency domain, it's frequency. And the vertical, we have amplitude for both. In the time domain, it's typically volts, although not always, but typically it's volts. The amplitude in the frequency domain is typically dB or dBm. So decibels or dBm or dB watts. Moving back to Sonic Visualizer, we said this top instrument was a time domain instrument, like an oscilloscope display. You can see the seconds running across the top. Here on the vertical is the amplitude. It looks like it's normalized between 1 and -1. This middle instrument is a spectrum analyzer. We have frequency running on the horizontal and amplitude on the vertical. And you'll note that it's in decibels. If you're musically inclined, you'll recognize this as a piano keyboard. So this note right here is C, C sharp, D, D sharp, E, F, and so on. In fact, if you look at this display, you can see that the trumpet is playing this note right here. It's playing a B flat, or A sharp if you prefer. You'll notice that there are many other peaks in this spectrum display. These are known as harmonics. The harmonics are what makes a trumpet sound like a trumpet. So if this is the fundamental frequency here of 464, we note this frequency is 928. If you take a calculator, so I've got my calculator here, so 928 divided by, go back here, 464, well, the answer is 2, because this note or this tone right here is the second harmonic. This one here is 1397, and we divide that by this one here, by 464, and that would be the third harmonic. So we have a fundamental tone, a second harmonic, a third harmonic, this is probably a fourth, and we have harmonics that are running all the way up into the 20 kilohertz range. Again, it's those harmonics that make a trumpet sound like a trumpet. While we're here, we may as well talk about this tool right here, which is known as a spectrogram. The spectrogram is a little bit of both oscilloscope and spectrum analyzer. You can see that there are peaks at the same time as you would see on the oscilloscope. For example, this piece right here, this sustained note on the end, appears like this in the spectrogram, which means time runs on the horizontal of our spectrogram. This is the frequency. It's as if we took the spectrum analyzer, which has an orientation like this, and rotated it. So those harmonics I talked about actually appear as bars. So they appear as these horizontal bars. And you can see the fundamental tone. Actually, let me zoom in a little bit here. Let's see if we can see it. All right, so here is the fundamental tone. And it's about, that's a little hard to tell for sure, but it's somewhere around the 470 kilohertz. Here's the harmonics. Here's another harmonic. And you can see those harmonics run all the way up to the top of the frequency band. While we're here talking about the two domains, let's make a note about applications. We could argue that the frequency domain is preferred for complex signals. For example, the frequency domain makes it very easy to calculate the bandwidth of a signal. We described bandwidth as the frequency 2 minus frequency 1. Here's an example. An FM broadcast might look like this in the frequency domain. It will have a center frequency, and I'm going to draw it as a wedge. So we talk about a wedge of frequencies. And we'll let this center frequency be 100 megahertz. The limit of the upper wedge will be 100.2 megahertz. And the limit of the lower edge will be 99.8 megahertz. Calculate the bandwidth. Bandwidth equals f2 minus f1. The understanding is that this is f2 and this is f1 in the frequency domain. So the bandwidth for this particular signal is 100.2 megahertz minus 99.8, which gives us a bandwidth of 400 kilohertz. Now that is something that would be very difficult to do in the time domain. But in the frequency domain, it's quite simple. Actually, let me back that statement up just a little bit. It's not impossible to calculate bandwidth in the time domain. It's just difficult because you have to infer what the bandwidth is. One of the tools, actually a tool that will be very important to us, is the Fourier series. That will be the topic of our next lecture. To help us better understand some of these concepts, I've loaded up another clip. In this particular one, it's called Emergency 911 Dispatch Call, and it sounds like this.
912 ambulance, 75-year-old male, back pain, 211 Silver Hollow Road, between Lane Road and Crosspatch Road. Repeating, 75-year-old male, back pain, 211 Silver Hollow Road, between Lane Road and Crosspatch Road. 0933 5632.
Okay, let's take a closer look at this. In the beginning, this clip has something called call tones. That's a form of digital communication that's used between the radios. And essentially what it is, it's an alert sound. It will wake up other radios. And you can change the tones to wake up different groups of radios. If we zoom in really far, we can see that that is a sinusoidal tone. It's not a perfect sinusoid, but it's pretty close. In fact, if we zoom in really far, we can see the dots. It turns out these dots are how the tone has been digitized and stored in the computer. So the computer doesn't store the music, it stores a discrete sample. So here's one sample, sometime later is another, and there's another. In fact, if you really wanted to know, the music is stored in samples such that we have a sample 44,100 times a second. But that's something we'll talk about later. For now, let's just assume it's a sinusoid. But at what frequency? Well, it turns out there are 3 different ways of determining frequency on this screen. In the time domain, let's see, looks like this would be a good place to start here. What you need to do is you need to find the time index for one cycle. So I'll get my calculator out, and you'll see this here is at 1.311 seconds. So that's 1.311 minus, now we have to go back an entire cycle, which brings us right here. So that's 1.309, it's not 95, it's 975. And that gives me an answer of 1 over 800. So that's the period. It's the time difference between here and here, which is what we did in the beginning. We figured out the period of the waveform, right? It's just the time difference. Take the reciprocal of that, and you end up with 800. So this appears to be an 800 hertz tone. In the spectrum analyzer, which is the middle instrument, it's really easy. You just go to it. It's right there. It's 800 hertz. Boom. That is what the frequency of that peak is. If we go to the spectroscope, same thing. We look for the bar right here in the bottom. And notice this guy right here where it says bin frequency. It looks like that bin is somewhere pretty close to 800. So 3 different ways of determining frequency. We can measure the amplitude by looking at this scale over here. In this case, it looks like the signal is plus and minus about 0.05. We could use the spectrum analyzer to talk about amplitude. In this case, we would talk about the amplitude of a very particular frequency. So this 800 hertz tone appears to be at negative 20 dB, which is probably relative to what full volume would be for this particular recording. The amplitude in the spectrogram is again red in this window here. So if we light up this section right there, we can see it's about negative 18 dB, which corresponds with what we see here, give or take. So that takes care of this tone, but it looks like there's 2 different tones in there, doesn't it? So there's a low frequency and then there's a high frequency. So if we go here and we zoom in, we can ask ourselves if that's a sinusoid. It appears to be a sinusoid. You can see there's some distortion in there, but it's mostly a sinusoid. As for the frequency, it appears to be 800 hertz. We can also come down here, 800 hertz. Again, amplitude here, amplitude in dB here, and amplitude here in the bin window. In the time domain, it's very clear that these 2 tones have different amplitudes. That amplitude is a little bit harder to tell here in the spectrum analyzer. This is the lower, right? It's the lower tone, but with larger amplitude. And it looks like it has a peak somewhere around negative 18 dB. This is the higher tone, but it has a lower amplitude, and it's somewhere around negative 22 dB. So that's a 4 dB difference, which in the time domain is quite a large difference, but when you're in the decibel scale, not so much. It's hard to tell that difference. Now let's look at the rest of the clip. That was a burst of noise, and you can see that it contains a wide range of frequencies, but there's no structure, there's no harmonics in there to speak of. Next, we see the voice.
912 ambulance, 75-year-old male, back pain, 211 Silver Hollow Road.
There's certainly some structure there. We can see bands of harmonics, and we can see from time to time that there are higher frequencies. Earlier, we played this clip, and we said the trumpet had harmonics. There were all of these bands of frequencies that made a trumpet sound like a trumpet. This is the sustained note at the end. You can see there's the note that's being played, second, third, fourth, fifth, and so on, harmonics. And we see those harmonics as bands in the spectrogram. But not all instruments are trumpets. Some things have very different sonic signature. For example, this song. Let's see if we can look at it and see what it'll sound like before we play it. All right, so let's go to the beginning. And let's zoom in on the spectrogram. And it looks very simple. Now there's a little bit of harmonic up here, but not much. So these are very pure tones that are being played. Well, I won't talk about it. Let's just give it a play and see what it sounds like. Unlike the trumpet, the flute has a very pure tone. And that's what we see when we zoom in, say, on this first note here. Now that we understand a little bit more about time domain and frequency domain, we can come back to this software-defined radio and look at BBC Radio 4 at 198 kilohertz. In this display, frequency is on the horizontal, the time is moving up, and the intensity or the amplitude of the signal is the intensity of the color. So the brighter it is, the higher the amplitude. The bandwidth can very easily be determined by looking at this frequency minus this frequency. And we can talk about filters. So we can open the filter to make it very wide. Ideally, you want your receiver to match the bandwidth of the transmitted signal. So you might set your filter to about this, which is 10 kilohertz.
Chamber of Deputies. The results ease the political pressure on Mr. Bolsonaro, who's been facing.
Our first step to understanding those filters is to go back to electronics class. Let's talk about phasers. Well, we'll do DC first, and then we'll pick up phasers. You remember this circuit where we had voltage in, voltage out. There was an R1 and an R2. And you determined using the voltage divider that the output voltage was R2 over R1 plus R2 by V in. And if you wanted to rearrange that, you could say voltage out divided by voltage in is that R2 over R1 plus R2. From our previous lecture, you remember that this is gain. Well, so-called gain. So-called because this is an attenuator, and technically an attenuator does not have gain. But we'll call it gain anyway, with the understanding that 0 is less than or equal to the gain of this attenuator is less than or equal to 1. So if R2 is open, voltage out will be equal to voltage in. If R2 is shorted, there will be no output voltage. So here's the question. What if we replaced R2 with a capacitor? We had a voltage in and a voltage out. The capacitive reactance is equal to 1 over 2 pi Fc. The impedance of the capacitor is equal to negative J by 1 over 2 pi Fc, which means that this circuit is now frequency dependent. That makes this class very different than our previous class. In electronics, we were content to let this be 60 Hertz. But as you can imagine, based on our previous discussions about radio frequencies, time domain, and frequency domain, frequency is going to change quite a bit. So no longer are we tied to 60 Hertz. However, since we're here, and since you'll need this information for the follow-on class, let's run the example at 60 Hertz. So let this be 1 kilo ohm, and we'll let this capacitor be 1 microfarad. So if we ran the calculation at 60 Hertz, we would say the capacitive reactance is 1 over 2 pi by 60 by 1 microfarad, which gives us a capacitive reactance of approximately 2700 ohms. The impedance of the capacitor is negative J by the reactance, which means the impedance is negative J 2.7 k ohm. Our voltage output as a vector is negative J 2700 over 1000 minus J 2700 multiplied by Vn. And V out over Vn is, let's see if we can still do that. So actually, be careful, make sure your calculator is back in complex mode. There we go. That is negative 2700J divided by 1000 minus 2700J, close, equal, shift to polar. That means the ratio to V out to V in, that's a V bar, there we go, is 0.94 at a phase angle of about negative 20 degrees. Let's see what happens when we do this at 1000 Hertz. Capacitive reactance is equal to about 159 ohms. Voltage out is equal to negative J159 over 1000 minus J159 by Vn, which should give us a voltage out, again those are vectors, voltage in of 0.16 at a phase angle of negative 81 degrees. So it would appear as frequency increases, the output drops, and the phase shift looks like it's going to negative 90. As frequency goes up, output goes down, and we have a phase shift. That isn't too surprising because as the frequency goes up, this capacitor acts more and more like a short circuit, which means the output will be less and less as the frequency increases. If we wanted to know more about this circuit, we could continue to grind it through our calculator. For example, here we have 60 Hertz, here we have 1000. We could try it again at 10,000, but that gets a bit tedious. Instead, we can shift to a simulation tool. such as multisim.com. Here's our circuit that we introduced earlier. It has an AC source, that 1K resistor, and that 1 microfarad capacitor. Something interesting is going to occur here though. This voltage source, I have it set to AC sweep mode, which means the frequency won't just be 1 kilohertz. It'll actually be a range of frequencies. So when we graph it, it looks like this. Now there's a bunch going on. Oh goodness, we don't need to go all the way up to 10 gigahertz. Let's try this, something different. So maybe only 50K. There we go, much better. Okay, so what we're looking at is the magnitude. So this is the magnitude, and this is the phase shift. So you can see as frequency, which is on this scale here, as frequency increases, we can see that the output decreases. And the phase shift starts out somewhere around negative 25 at the lowest frequency here, and then appears to steady out at negative 90. Let's start with what we know. Earlier, we did a calculation at 60 hertz. So if we look on this graph, here's 100 hertz, so 60 hertz must be down here somewhere, so 9876. So that would be this first one right here. And because of the way this tool works, it looks like 62 hertz is as close as we're going to get. And that'll be fine. It tells us that the phase shift is negative 22 degrees at 62 hertz, which is very close to what we calculated. I believe we calculated negative 20. The magnitude is here. Now we calculated 0.94. This tells us it's 0.93. So we're in the neighborhood there. We did a calculation at 1 kilohertz. So let's see if that holds. So our calculation at 1 kilohertz said negative 81, and that matches. And it said our amplitude was 0.16, which again is very close to what we see in this graph. This is a filter. This filter attenuates all of the high frequencies. If the frequencies are low, the output is very close to what the input is. As the frequency increases, it drops off. We can play with the various values. For example, if we take this capacitor and we lower it by 2 orders of magnitude, so 0.01 farads, and then we run the simulation again, with that new capacitor in, you can see that the output is almost identical to the input until we get into about the 10 kilohertz range. Then we see it start to drop off here. The phase is almost identical, which is to say there's no phase shift input to output until we get into the kilohertz range. Now let's do something interesting. Let's go back and let's break these connections and swap the place of these parts. So we'll put the resistor there and the capacitor there. Okay. Now when we run it, we're going to get a different shape. So it looks like our phase starts out at negative 90 and then progresses to 0. But here we're attenuating all of the low frequencies until we get into the tens of kilohertz, and then it looks like we settle out on 1. This would be known as a high-pass filter because it passes all of the high frequencies but attenuates the low frequencies. Whereas before, we had a low-pass filter. It would allow the low frequencies to get through, and it would attenuate the high frequencies. There is another type of filter I'd like to show you, and that's known as the resonant circuit. Let F equal 10 kilohertz. We know that the capacitive reactance is equal to 1 over 2 pi Fc, And we know the inductive reactance is equal to 2 pi FL. What would happen if we set these two equal to each other? So if we let 1 over 2 pi FC equal 2 pi FL. In fact, let's let F be 1K, and let's use that 0.1 microfarad capacitor we had earlier. So 1 over 2 pi, we said 10K, and we said 0.1 microfarads is equal to 2 pi by 10K by L. Solve for L. And if we do that, we find out that L is equal to 2.53 millihenries. Let's see what that looks like in the simulator. Before I forget, let's change this capacitor. We said 0.1 microfarad. Let's add an inductor. We'll let this be our output voltage right there. And as far as the inductor value is concerned, let's put in the value we just calculated. So that's 2.53 millihenries. And let's see what we get when we run the simulator. Now, that's interesting, isn't it? At 10 kilohertz, the output is equal to 1. So we have unity. Voltage out is equal to voltage in. However, if we drift off frequency, we can see that we attenuate the low frequencies and we attenuate the high frequencies. This is what's known as a band pass filter because it'll only let these frequencies get through. If we go back to the schematic and we change it ever so slightly, we put that inductor here, and we let this be voltage out. When we run the simulation, we have the exact opposite. The low frequencies are allowed to come through. 10 kilohertz is not allowed to come through, but the high frequencies are allowed to come through. This is what's known as a band reject or a notch filter. Effectively, what we've done is we have notched out the 10 kilohertz signal. The textbook would call this a series resonant circuit, where the capacitive reactance and inductive reactance are equal to each other. And this was a parallel resonant circuit. Once again, where the capacitive reactance and inductive reactance were equal to each other. As we finish up, let's just make a few notes to capture all of the different types of filters. There was the high-pass filter. In the frequency domain, that filter would allow the high frequencies to pass. So this is called the pass band. Were we to make a block representing that filter, it would look like this. High frequencies, mid frequencies, low frequencies. The high pass filter allows the highs to go through, but it rejects the mids and it rejects the lows. It only lets the high frequencies get through. Next is the low pass. In the frequency domain, this is the pass band. In block diagram form, it only lets the low frequencies through. So we put an X over the high frequency, we put an X over the mid frequency. Next is the band pass. In the frequency domain, it looks like this. As for the block, we attenuate the high, we attenuate the low, only allowing the mids to get through. By the way, we did talk about receivers, and we talked about the bandwidth. And on that example, we could move the bandwidth or reduce the bandwidth. We do that with a band pass filter. So this would be an F2, and this would be an F1. And we can talk about the bandwidth of the bandpass filter. With a little bit of imagination, you could visualize this bandpass filter sliding up and down the frequency domain, and by doing so, you're able to tune the radio receiver. The last filter is a notch, otherwise known as the band reject. In the frequency domain, it allows the low frequencies to pass, it rejects the mids, and it allows the highs to pass. So it has a notch. In block form, highs, mids, lows, the band reject will attenuate the mids. As for how to actually build these filters, there are many different ways. There's the passive filters that we explored. And those are the resistor, inductive, capacitor circuits. You could make active filters. For those, you would use amplifiers and the R, L, and C components. So here's our triangle for an amplifier. And then again, we would use R, L, and C as appropriate. You could have mechanical filters, where something mechanical resonates at just the right frequency. You have crystal filters, where a piezoelectric crystal will vibrate at the frequency of interest. You can also have digital filters. For this class, I'm afraid that these types of topics are a bit beyond the scope. However, we will pick up the concept of digital filters sometime mid-semester. To answer your question about which filter is best, well, like everything else, the best filter is the one that will do the job for the least amount of money.